In the first part of the Gas Laws lab, we investigated the relationship between pressure and volume of a gas in a sealed container. Our data and observations led us to develop the law: at a constant temperature and number of particles, pressure and volume are inversely related. Pause the video for a moment and record our new law in your notes. Now let's apply this law to solving gas law problems. In example number 1, a diver blows a 0.75 liter air bubble 10 meters underwater. As it rises to the surface, the pressure goes from 2.25 atm to 1.03 atm. What will the volume of air in the bubble be at the surface? Let's complete our ice table with this new information. Liters is a unit of volume, so my initial volume is 0.75 liters. Meters is a unit of distance, so this is extra information that I don't need to solve this problem. The initial pressure is 2.25 atm, and the final pressure is 1.03 atm. We are solving for the new volume of the bubble. If we look at our law, when pressure decreases, since it's an inverse relationship, volume should increase. We start our problem solving with the volume measurement, since this is the variable we are trying to find the change in. And we're going to multiply that by a proportion using our pressure readings. Since we want the volume to be higher, we need to put the larger number on the top of our proportion. So it'll be 2.25 over 1.03. When I type this into my calculator, I get a long decimal point of 1.6384. I need to round for sig figs though. I look back at my ice table and I'm limited to 2 sig figs based on the volume, so my final answer is 1.6 liters. Let's do a second application of the pressure and volume law. This time we have 20 liters of a certain gas at a pressure of 2.1 atm. The gas is injected into a 40-liter tank and we need to determine the new pressure of the gas. Liters again is a unit of volume, as we learned from our first unit of the year. So we have 20 liters as the initial volume. The initial pressure is 2.1 atm. The gas is injected into a larger volume tank of 40.0, and we need to determine the new pressure. I forgot to mention in the previous problem, if temperature is not mentioned or number of particles, we're going to assume those variables remained constant. Alright, so the volume in this system increased, and based on our gas law, if volume increases, the pressure should decrease. Okay, we start with our initial pressure reading of 2.1, and we're going to again multiply it by a proportion. This time we want a lower result, so we're going to put the lower number on top of 20, and then 40 in the denominator. When I type this into my calculator, I get a result of 1.05. I look back at my ice table and I'm limited by the pressure reading and the number of sig figs, so the correct answer, I would round it to 1.1 and the units are atm. In the second part of the lab, we were investigating the relationship between pressure and number of particles of a gas in a sealed container. As we added puffs of particles to the flask, we noted that the pressure increased and we saw a linear relationship on our graph. So we will summarize that in our Adams family pressure and number of particles law. At a constant volume and temperature, pressure and number of particles are directly related. Pause the video now to record this law in your notes. Now let's apply this law to a gas law problem. A syringe contains 15 units of air particles with a pressure of 1.77 atm. The plunger is used to push 5 units of air out of the syringe, and we need to determine the new pressure. Let's complete our ice table with the information in the problem. We're starting with 15 units of air and an initial pressure of 1.77. The plunger is used to push out 5 units, which means the final number of particles would be 10, 15 minus 5. And we're trying to determine the new pressure. Again, the temperature in the system must remain constant and the syringe has a constant volume. The number of particles clearly decreased, and according to our new law, there is a direct relationship between number of particles and pressure, so the pressure should decrease as well. We begin with the pressure value of 1.77, and again we're going to multiply that by a proportion. Since we need our final pressure to be lower, we're going to put 10, the lower number, on the top, 15 in the numerator. And as I punch this into my calculator, I get a result of 1.18. As I look back at my ice table, I am limited by the number of sig figs and the initial units in the syringe, and so I'm going to round this to 1.2, and the units are ATM. In part 3 of the lab, we investigated the relationship between pressure and temperature of a gas in a sealed container. We noted that at a constant volume of the test tube and a constant number of particles, the pressure and temperature in Kelvin are directly proportional. So when applying this law, Celsius needs to be converted to Kelvin. Pause the video to take a moment to write this new law into your notes. Now let's apply this law to solving gas law problems. The pressure of oxygen gas inside a canister is 5 atm at 25 degrees Celsius. The canister is located at a camp high on Mount Everest. If the temperature there falls to negative 10 degrees Celsius, what is the new pressure inside the canister? Okay, as we complete our ice table, the initial pressure of the canister is 5.00 atm. The initial temperature, again, we need to change from Celsius to Kelvin. So we take 25 degrees and, per this equation here, add 273 to get an initial temperature of 298 Kelvin. If we take the canister to the top of the mountain, the temperature is now negative 10 degrees. Again, we add this to 273 for a final temperature of 263 Kelvin, and we need to determine the new pressure. Volume and number of particles are constant in this relationship. If temperature decreases according to our new law, the pressure will decrease as well. Beginning with our initial pressure of 5.00, again, we're going to use the temperature values to create a proportion. We need a lower pressure, so I'm going to use 263 in the numerator and 298 in the denominator. The result on my calculator is 4.4128. Looking at my ice table, I am limited to 3 significant figures based on all of my measurements, and so I'm going to round this to 4.41, and then our units, again, of pressure will be atm. Let's look at a second example of our gas law relating pressure and temperature. We have helium gas this time in a 2-liter cylinder, and it is under 1.12 atm of pressure. At 36.5 degrees Celsius, the same cylinder has a pressure of 2.56 atm. What was the initial temperature of the gas in the cylinder? Okay, as we begin to go through our data, liters is a unit of volume, so I'm going to put that in my initial volume column. And that gas is under a pressure of 1.12 atm. At 36.5 degrees, so normally I would think that that was the initial temperature because it was given first in the problem, but as I was reading I found that we're actually solving for the initial temperature. So 36.5 degrees Celsius is my final temperature. Again, we need to convert this to Kelvin by adding 273, which gives us a final temperature of 309.5 degrees Kelvin. Okay, the only number we haven't used is our new pressure, which is 2.56 atm. Now they mentioned the volume of the container, but it must be a rigid container, so volume is constant, and that was just extra information. And if it's a closed system, number of particles would be constant as well. Okay, so the pressure clearly increased, which if you look up above at our law, that means that the temperature should increase as well. However, this is a unique situation in which we're trying to solve for initial pressure or initial temperature. So we actually need to flip our calculation around. We're going to start with the 309.5 degrees Kelvin. Again, multiplying it by a proportion. Even though normally we would see temperature increase, we need the initial temperature, so we're going to set it up for a smaller result, meaning that the pressure should be 1.12 on the top and 2.56 on the bottom. When I perform this calculation, the result is 135.406. Before I round, I want to make sure that my answer makes sense. Again, I should see if pressure increases, temperature increases as well. If this was my initial temperature, 135, and my final was 309, it does obey my law, so I have done the calculation correctly. Of the information I used in my calculation, I need to round to 3 significant figures, which would be 135 Kelvin. Now, there was no mention if the answer should be in Kelvin or degrees Celsius, so I can leave this as my answer, or by subtracting 273, I can change this value back to Celsius, which would be 137 degrees.